Any questions about final projects? Any questions about the policy statement from it? Yes? You could do Wi-Fi if it'll fit in your budget. You can buy a Wi-Fi transceiver with TCP/IP stack for about $38. So yes, you can do it. You can't do two of them. So yeah, I'd like to see that happen because I'd like to buy a whole pile of those and use them for one of the routine labs next year. It's time. It would be really nice if we could have everybody's Lab 3 be on Red Rover. I don't know if Red Rover would like that. But. Any other questions? Any questions about the policy stuff we talked about last time? Okay, as of this morning, the lab statistics are 33 in Wednesday night, 19 in Wednesday, 19 in Thursday, and 30 on Friday. That's pretty good. I'd like to get a couple of more, perhaps 3 or 4 more out of Wednesday into Wednesday night into Wednesday afternoon or Thursday. I'd like to get a couple more out of Friday. But experience shows that that the number of people that end up in the class is approximately the number who pre-register. 84 pre-registered, 102 showed up on Monday. Registration is now down to 101. One person bailed, which is less than I expected, actually. So we'll see it if this number falls back. I'm not sure it'll fall all the way back, but I'm okay with these. TAs I forgot to introduce last time. Mike, Pavel, Ninoshka, and Joe. Joe here? Joe is here on Monday. He's not here now. And there'll be a grader who will be in charge of making sure that the grades are all recorded, cracking the whip over the TAs, so that they do the grading and get the grades to him. It'll be Human, I forgot his last name, and but his name's on the web. And if you want to find out what a grade is, you will email him. Actually, we can't send grades by email. You have to use Dropbox. Cornell. Dropbox.cornell.edu. All grades have to go by Dropbox because that's considered secure. Email is not secure because anybody can spoof an email header. Okay, let's start talking about the gory details. It's time to start talking about Lab 1. Oh, I already had a question on homework for Lab 1, which I really appreciate. That's nice. Actually, somebody's reading the homework. Awesome. And the question was, what in the world does this mean? OCIE0A. That's a homely piece of code, C code. This is a constant which is predefined in io.h, and in this case has the value of 1. So this says take 1 and shift it 1 to the left. In other words, it sets bit 1. It's just an interesting way of naming bit 1. You'll see it a lot. Were there any other questions about homework 1? It's not too early to start. Okay, so I think I said last time GCC is Nancy Standard C. There's specific hardware libraries that are available, I/O libraries that are available for this architecture. For instance, standard I/O is available. So there's a print, and a scanf command, as there is in almost all variants in C. And even though there's no Unix running, there's no operating system running, the C compiler simulates enough of the I/O system so that you can print stuff to a terminal. You can receive information from a standard terminal like Hyperterm or PuTTY. There is a library to run the liquid crystal display, put string, put car, so on. There are some very skeletal interrupt service routine features that we'll have to fill in by hand. Everybody knows what an interrupt service routine is, right? And even though this is an 8-bit microcontroller with no floating point unit, there is a floating point library for it. In fact, there's 2 or 3. And the speed of the floating point depends on which library you happen to link, and the default library is not the fastest. But that's okay because you'll barely use floating point in this course anyway. Almost everything will be fixed point for speed. It takes about 150 to 400 cycles to do a floating point multiply. Microcontroller we're going to use is a Atmel Mega 644. And you ask, why 8-bit? Well, it's cheap, and therefore I can afford to buy enough of them that you can afford to blow them up. That's also why we use PDIP package, because when they've become toast, you can pop them out and put a new one in. Whereas if it's surface mount, you're stuck. We blow 40 CPUs a semester, something like that. That's just what happens. You short an output port to ground, it's gone. It's really easy to do. Another reason that we use 8-bit microcontrollers is probably the majority of CPUs sold in the world are still 8 bits. About 4 or 5 billion a year. Another reason is that the clock speeds on these 8-bit machines are fairly low, about 16 to 20 megahertz, which means you can still use wires to hook them up to stuff. You can use 18-inch wire and still be reasonably sure that you're going to get a result back within 1 clock cycle. So it's a nice speed for interfacing. And there's 32 I/O lines. There's 4 I/O ports. That's enough to do a lot of stuff. There's some nice battery saving modes. There's some nice power down modes on these little processors, so that if you're building something that needs a long battery life, piece of instrumentation that's going to live on your body or something of the sort, then it's fairly easy to get the power supply use minimized. And it's really easy to make these things go standalone. They have internal oscillators. If you turn on the internal oscillator, you can take the CPU, you put a 3-volt battery across ground and VCC, and it'll boot and run. That's all it takes. Everything's inside. It's completely self-contained. It makes it really easy to build a standalone target system. Or if you want to use 16 of them to make a crossbar switch or some crazy thing, then you can do that too fairly easily. And they can be programmed about 10,000 times, which makes them awesome for a teaching lab. However, they will get used up this semester. Some of these will be programmed more than 10,000 times, and they'll stop taking a program. And when that happens, you're going to have the TA help you figure out what's wrong and get a new CPU. I would prefer you not to change CPUs on the prototype board yourself for the first couple of labs, because experience shows that almost nobody knows how to unplug a 40-pin PDIP without bending the pins. And I would like to show you how to do that before you bust up a bunch of them. So there's 32 I/O lines, 32 digital I/O. There is no analog I/O on this chip. However, there are six PWM channels, pulse width modulation channels. A pulse width modulation channel fed through a low-pass filter is an analog output. So there's 6 PWM channels. There's 3 hardware timers. And as you probably know from 3140, you can never do accurate timing in software. You have to do it in hardware. Software is just too hard to balance. It's too hard to cycle balance. It makes it unmaintainable and unreliable. So we'll be always, every single lab, every program you write in this class will use at least one of the hardware timers. There's an A to D converter, 8-channel. It's fairly slow. You can get 10 bits at 10 kilohertz, and but you can degrade this gracefully. If you only need 5 bits of resolution, you can run it at least 30 kilohertz. So you can trade off bits of resolution for conversion speed over a fairly large range. There's a UART. How many of you in your life have ever used a serial terminal for anything? Cool! Was that done in 3140? No. Yes? No. All right, so you know a little bit about serial terminals. So there's a device that allows a serial control stream, we'll talk a lot more about this, to be interpreted into parallel words. It's called a universal, actually USART, Universal Asynchronous Receive Transmit. It's a serializer, deserializer. There's an interrupt on every I/O line, which you can set up. There's an interrupt, several interrupts on each timer. There's about 35 interrupt sources. There's SPI, there's Serial Peripheral Interface, which is a high-speed serial synchronous communication standard as opposed to asynchronous. So there's a clock that's associated with this, and we'll probably be using that later in the semester. There's a watchdog timer. You know about those from 3140, watchdog timer? This is a device, if all else fails, if your system hangs, the watchdog timer will reset it and get the code running again. And this would be important in some context. Let's say that you have a microcontroller which is controlling a radiation gate on a therapeutic machine, and that pulls the gate open and then crashes. And so you got this X-ray beam hitting the patient. It'd be really nice if the system resets and turns off the beam. So a watchdog timer could be considered a safety device or a fail-safe device of various sorts. There's a gigantic 4K of RAM. That's data storage. There's 64K of program storage, which is flash memory. There's 2K of EEPROM. And just to make things annoying, accessing each one of those requires a different pointer structure. And therefore, the read-write commands for each one of these are different. But we'll show you how to do that as time goes on. So each peripheral then, each timer, each I/O line, so on, has some control registers, as usual. Timer 0, the simplest control timer 0, has 6 control registers. TCCR0A, TCCR0B, TCNT0, OCR0A, OCR0B, and TIMSK0. T-count 0 is actually the counter which maintains the tick, which maintains the count of how many clock cycles have passed. These are control registers for setting up various combinations, because what you have here is really a timer toolkit. It not only times intervals, you can set up the timer to toggle an I/O line periodically. Therefore, you can make a square wave without any software. You can also set it up so that when the count matches the compare register, the count automatically is reset to 0. TIMSK0, the time mask, sets which of these various events, overflow, matching these two registers, and so on, triggers an interrupt. Anything can be interruptible. And we'll talk about this in horrible detail. So now, starting to talk specifically about Lab 1 for next week. First lab is next Wednesday. It's going to be, of course, an introduction to the compiler and the proto board and I/O registers, but it'll also be the first half of building the reaction time timer, which will be finished in the second part of that will be the next lab. And we'll basically be using two pieces of the microcontroller. There'll be an I/O ports and timer 0. There's 4 I/O ports, amusingly labeled A, B, C, and D. And you can look up the special functions of each one of them, but they all act like general I/O ports. You can set any bit of any port to be an input or an output within one cycle. So there is a data direction register for X, where X takes on the value A, B, C, or D. So there's a data direction register which takes an 8-bit value and sets the I/O direction for each pin, a 1 being an output. Then there is a register called, an I/O register called port X, which when you write to it, sets the port. If the data direction register is set to a 1. There is a pin X, so this output is the port X, and this is pin X.Y. The pin register contains the inputs. If you set the data direction register to an output and set the port register and then read the pin register, what do you get? The value you just set in the port register. So these 3 registers control the I/O, each I/O pin independently as a logic level. For Lab 1, after we go through this, I want to talk a little bit about interrupts, and then we'll start in with some actual C code, which, by the way, you may want to look at before we go through it in class. There are 3 examples in Lab 1. We'll go through them all in the next week or so. We're going to be running, for the first labs, we're going to be running the processor at 16 megahertz. Oh, and by the way, at the end of the semester, people tend to swap out crystals for any random value they think is going to be useful for their final project. So some of the CPUs might have 7.14 megahertz crystals, some might have 14.2, some might have 22 if they're overclocking. And so you're going to need to check the crystal on your board every day to make sure it's a 16 megahertz crystal. It's a good idea because the crystals fall off the board regularly anyway. And you'd be surprised at how many times people call me over and say the board mode program, the CPU doesn't seem to be running, there's no crystal on it. So you can save, you know, the embarrassment of that by checking for the crystal. This is also the master control frequency for the timers. Now for lab 1, we're going to do a prescaler of 64. So we're going to do a divide by 64. So 1 tick then of timer 0 is going to be 4 microseconds. And so 250 ticks will be 1 millisecond. And we're going to time a lot of the processes. We're going to time kind of the world's crudest round-robin scheduler off of this 1 millisecond tick. So timer, yes? Prescaler. Let me write it. Let's divide by 64. So we're going to set up timer 0 so that it starts counting up. When it gets to tick 249, it gets reset to 0. We're going to use the automatic reset function, so it doesn't require any software to reset the counter. It does it in hardware within 1 cycle. Counts up again, reset. So we're going to have to turn on the automatic reset. So we're going to have to turn on auto reset. And we're going to have to turn on a separate bit, which is interrupt on match. Auto reset on match. Interrupt on match. And that'll allow us to interrupt the CPU at a 1 millisecond rate, which will be very useful for kind of human scale timing, since one of the things you're going to have to time for lab 1 is your reflex time, which is going to be in the probably the low hundreds of milliseconds. But certainly a resolution of 1 millisecond is good enough, since nobody's, I won't say nobody will be below 100 because somebody will be. But it's unlikely that you're below 80. Did anybody look at that video, by the way, in lab 1? That's insane. Guy's so fast. All right, so go into a little more detail on timer 0 then. Of course, the center of the thing is T count 0, which is a register that is clocked off of a mux, which has as inputs the outputs of a divider, which is being clocked at 16 megahertz. The outputs of the divider can be divide by 1, divide by 8, divide by 64, 256, and 1024. Plus a couple of other things off, and I guess that's all for that. So we have all of these inputs to the mux, plus we have another input which is called T0, whose logical name is T0, and its pin number on this particular chip is port B.0. So it's port B, pin 0, is a clockable input to timer 0. That's for measuring external frequency or events or whatever. This mux is controlled by TCCR0B register, bits CS02 down to CS00. There is a separate register, OCR0A, output compare register, timer 0, channel A. The output of this register is compared in hardware. There's a hardware comparator which detects equality. And on equality can be set up to do several different independent things. For instance, it can clear T count 0. It can also set an interrupt flag. In other words, it'll force a hardware event on the CPU. It can also toggle an I/O line. These are both readable and writable from the I/O bus. There's a separate channel, another equality detector with a OCR0B, output compare register, timer 0, channel B. This output can set an interrupt and toggle an I/O line, but it cannot clear, it can toggle an I/O, but it cannot clear T count 0. It makes no sense to have two possible registers that can both clear the counter because the lower one will always win. So, so there's, and this is timer 1 is more is slightly more interesting. It first of all, it's 16-bit rather than 8-bit, and it has a input capture function which allows you to grab the cycle accurate time that an external event occurs, which will be very useful, in fact essential, for measuring the frequency for the frequency meter in lab 2. But for right now, we'll stick with the 8-bit timer that we're going to use as kind of almost in every lab as a utility 1 millisecond time base. Any questions? Say again? To this divider, it's going to be the 16 megahertz crystal. So it runs off of the system crystal. The 16 megahertz, it is a piece of quartz that when you hit it rings like a bell at 16 megahertz. And the way you hit it is it's piezoelectric. So you hit it with a pulse, it makes a pulse. You feed that pulse back, it oscillates. So it's a mechanical oscillator. It is exactly a spring mass oscillator tuned to 16 megahertz within 0.005%. 50 parts per million. It's not good enough for a wristwatch, but it's not bad. How good's your wristwatch? Parts per million. Assuming you're not on, atomic time from WWV. It's probably 5 to 10 parts per million. Yeah.
What's a mic?
What's a multiplexer?
Oh, okay. I've never heard that.
Oh, okay. You've heard multiplexer. Okay. All right. You scared me there for a minute. Okay. Anything else? Any other? Jeremy.
If you're using the internal oscillator, is there like another box that's determining what frequency is feeding into the divider?
If you use the internal oscillator, then the internal oscillator feeds this instead. It's whatever the system clock is.
So when you set it in the fuses, there's another Luxa determining what's feeding into it?
That's correct. Right. So, as Jeremy implies, there's several clock sources that are available, including an external clock source and an internal clock source, which can be set to a few frequencies and also trimmed through I/O registers. I tend not to use those because they're only on this chip. They're only good to about 1%, which is barely good enough for a lot of stuff. And the external crystals are much more reliable. On the other hand, if you need to go to a very low power system that doesn't need lightning response, then the internal oscillator can be set to about 1 megahertz and cuts down the power by what factor? Over 16 megahertz. About 16, right? Because it's CMOS. And almost all the power dissipation is capacitive, which is proportional to the clock rate. So instead of taking 30 mils, it takes 500 microamps. Anything else? Those 3 bits are what drives that multiplexer setting. Sorry. All this is in the data sheet too. Now we go down the next layer and we say, all right, what is this TCCR0A? What are the bits in the control register A? These have really obscure names. These 2 bits are COM0A1 and COM0A0. These are named similarly. And what they do is connect timer 0 to I/O pins, to 2 I/O pins. I'm not going to talk about them right now for Lab 0 because we don't need them. This bit 1, is referred to as WGM01. I don't even know what that acronym stands for. WGM1. Has anybody read enough of the data sheet to know what that stands for? Waveform generation module? Mode. All right, cool. All right. Thank you. This sets auto clear on match. So this sets auto clear on match. And the implication is OCR0A, on matching OCR0A. And this bit does something else I don't want to talk about. But we're going to need to set this one to 1 for Lab 1 because we're going to need it for precision timing. And the way we do that is say TCCR0A is equal to 1 shift shift WGM01. All right, so TCCR0B then has in it CS00, CS01, CS02. That being the bits that control the mux. So this is rate control or prescaler. Prescaler rate. And then there's a bunch of other stuff in there I don't want to talk about for right now. So what we're going to do for lab 1 is we're going to set TCCR0B equal to 3, which happens to be divide by 64. Again, you have to just go through the data sheet and paw through all of the description of lab 0 to figure out what you should set it to. There's a chart in there that says that if you set this register to 3, that the prescaler will be 64. Then we're going to set OCR0A to 249 so that we have a periodic count of 250 ticks because it's zero-based, which I got wrong for years. Until I took a stopwatch to the system and timed it for long enough to see 1 part in 250 inaccuracy. It doesn't take that long. Only takes 5 minutes. Oh, and one more register. Any questions, though? Okay, we have one more register, which is TIMSK0, the time mask, which is where we're going to set the interrupt modes, which are active. Now, there's a really obscure bug that happens. If you turn on a bit in a time mask for which you have not written an interrupt service routine, because the hardware will take the interrupt, and where does it go? There's no interrupt service routine. Did I see a hand up? Yeah, go ahead. Whatever's in the vector table. Whatever the compiler decides to put in the vector table. And does anybody know what that happens to be for GCC? It's reset. And so the symptom will be, I don't understand it. My CPU is resetting 10,000 times a second. Aha! The first thing that should come into your mind is, I turned on the wrong mask bit. That should be hardwired in your hardware. Bit 0 is timer 0 overflow. T0 IE0, they call it. Bit 1 is OCIE0A. It's the overflow, or it's the output compare interrupt enable timer 0 channel A. And then we have the output compare interrupt enable timer 0 channel B. This being channel A, channel A, this being channel B. So there's 3 possible interrupts only, 3 possible interrupts for timer 0. For this lab, you will turn on exactly 1. If you turn on more than 1 and do not write an interrupt service routine, the system will apparently stop, except it's actually resetting. It is the overflow interrupt. So if you just let this, if you don't turn on the auto clear, and you just let this thing count up, it'll count up to 255, overflow to 0, and start again. And that could be useful. But in this case, we're not using it. Timer 0 is an 8-bit counter. Timer 1 is a 16-bit. Timer 2 is an 8-bit. So timer 0 only counts up to 255 and then rolls to 0 and starts again. So to make this thing work right, to make the 1 millisecond timer work, you have to turn on the clear on match and set the interrupt on match. You have to have both of these bits set so that it clears and then sets. Otherwise, it'll set the interrupt. It'll interrupt after 250, after 249, and after that it'll interrupt after every 255 cycles, because it'll roll completely around and catch it again. So everything in the class we're going to be doing is a real-time operation. There's going to always be a deadline. Some are more demanding than others. Lab 1 doesn't have a very demanding time deadline because really we're only going to be making decisions about once a millisecond, and you have about 16,000 cycles in a millisecond. So you could do a lot of fixed point in 16,000 cycles, make a lot of decisions, write a lot of stuff on the LCD. Actually, you can't write a lot of stuff on the LCD in 1 millisecond because the LCD takes 1 millisecond per character. It's really slow. It's 9,600 baud equivalent. So, so you need to think ahead a little bit about that. But later in the semester, when you're doing the sound synthesizer, you'll be looking at a sample rate of 8,000 or 16,000 samples a second. So you'll be taking 8,000 interrupts a second, each of which has a lot of code in it. And so everything we do is going to have a deadline. It's going to have a deadline that you have to meet, or you'll get bad sound out, or the timers won't work, or something else will happen. And so the course is completely real time, so to speak. And sometimes we'll want to make an event happen. Sometimes we'll want to measure a frequency. Sometimes we'll want to count external events. And we just can't do this in software. We're going to have to depend upon hardware interrupts. So I want to talk just a little bit about the interrupt structure on this box. It's pretty simple. Low memory, 0 through memory position 30 or so, has a table. So low memory, this being flash memory now, program memory. Low memory has a table of interrupt vectors. Vector 0 is always reset. And I got to tell you, I don't remember what the next one is. I think it's external interrupt. And so on. Each one of these contains the address of an interrupt service routine which you must write. If you don't use the interrupt and you never turn on the interrupt flag, you don't have to write the interrupt service routine. Generally what you're going to do is you're going to have some init code in which interrupts are off. And while the interrupts are off, you're going to set up the tables, you're going to initialize timers, you're going to do all this kind of bookkeeping you have to do, which you have to do before you turn on an interrupt and start taking bizarre events which may not be defined yet. So you do a bunch of initialization with interrupts off. Then you turn on the master interrupt bit, which is the I bit in sreg. You turn on the I bit in sreg, and there's a C macro that does that for you. Then you drop into some slow background code. And you execute this forever. And of course, like every microcontroller, you never exit main because there's nothing to exit to. Right? There's nothing. So you never exit. Meanwhile, interrupt-driven tasks are going to be asynchronously called from main and because they're asynchronous, it implies, of course, that there are no parameters. No parameters. Interrupt tasks, interrupt functions can have no parameters. They cannot return a value, no return. And they must, of course, save the CPU state. Because they are completely asynchronous, they can happen anywhere. Now, C does that part for you. C saves the state of the CPU on when a hardware event occurs. And remember, this is hardware events here. If you don't do anything, if you just define an interrupt service routine, which we'll show you how to do in the next lecture, then it takes about 75 cycles to get in and out of an interrupt service routine. It takes about 32 cycles to save the state of the machine, 32 registers going in, 32 cycles coming out, plus 7 or 8 cycles overhead we'll talk about in a minute. So it's a fairly slow thing. You can turn off the auto save on the interrupt service routine if you're willing to write the interrupt service routine in assembler. You can put it in so-called naked mode, and in that case it doesn't save any registers, it does nothing, it assumes you know what you're doing. I'd say for the first couple of labs, don't do that. Unless you like putting holes in your foot, shooting your foot. So, some event occurs. Some hardware event. Maybe a timer goes off. Maybe there's a character that arrives on the USART. And the hardware event sets a flag. You have access to those flag registers. It's 15 after, or is it 10 after? Oh, it's 10 after. Oh, I'll stop now. Thank you. I keep thinking it's 15 after. Any questions? All right, see ya.